At this point, we have looked at various radiometric concepts. We understand how to describe the brightness of a source by its radiant intensity, the illumination of a surface, which is the surface irradiance. The brightness of a surface is given by its radiance. We also looked at the bidirectional reflectance distribution function, which describes the ability of a surface to take light from one direction and scatter it or reflect it in another direction. And we looked at various types of reflectance models that are commonly found in practice. So now, with all that in place, we are ready to develop our first method for recovering three-dimensional shape information from image intensity values. And this method is photometric stereo. First, let's take a look at the factors that affect image intensity. Let's say you measure one intensity in an image. What are the factors that drive that intensity value? So here is your typical setup, imaging setup. You have a camera with a viewing direction V. We'll assume that the viewing direction is aligned with the z-axis of your coordinate frame. And we have a single light source here. We're going to assume for our purposes here that you have a single point light source, which is in the direction S. S is a unit vector. It has a certain brightness, it has a certain distance from the surface itself. And the point that we're looking at has a surface orientation, which is described by the normal vector, unit normal vector n. So image intensity is a function of the source. Once again, the source is given by its direction, its radiant intensity, its distance, and it is determined by the orientation of the surface n, which has a couple of parameters associated with it, and last but not the least, the reflectance properties of the surface. And that could have several parameters or a small number of parameters depending on how complex the bidirectional reflectance distribution function is. So in this lecture, for developing photometric stereo, we're going to assume that we know the source or the illumination. When we say that the source is known, we're going to assume that we know not only its direction, but its radiant intensity and distance as well. We're also assuming that it's a point light source. And this point light source is distant from the surface. What does that mean? It means that as you walk around on the surface, you're going to be seeing the source in the same direction if the source is distant. And we're going to assume that we know the reflectance properties of the surface. That is, we are in a structured environment where we have access to information such as the reflectance properties, and we can control the lighting, and therefore we know the source direction. And of course, we've measured an intensity value in the image. So I is known, the source is known, and the reflectance properties are known, and what we seek to estimate is the surface normal at each point on the surface. So that is really what photometric stereo does. Photometric stereo is a way of computing, estimating the surface normal at each point on a surface, given its reflectance properties and given information about the light sources. And it turns out, in order to solve this problem, we need more than one image, more than one light source. So photometric stereo uses multiple light sources, captures multiple images, and then from this stack of images, it's able to compute the surface orientation at each point. So first, we're going to start off with what's called the gradient space. The gradient space gives you a convenient representation for the orientation or surface normal at each point on the surface. And then with the gradient space in place, we're going to talk about the concept of a reflectance map. It's a representation. The reflectance map gives you the mapping between surface orientation or surface gradient and the intensity that a point would produce. So the reflectance map assumes that you know the reflectance properties of the surface, you know everything you need to know about the light source, and then given a surface orientation, it tells you what the corresponding image intensity would be. So with that in place, we can develop photometric stereo. And we see that if you're given one intensity value, which is measured using a single light source, there are an infinite number of surface normals or surface gradients that would have produced the same intensity value. And so to resolve this ambiguity, we use multiple light sources. And then we find that we can, with a small number of light sources typically, uniquely determine the surface normal at each point on the surface. Now, there are circumstances where we can write an expression for the reflectance model of the surface. We know what we are dealing with, we know that it has a simple form, and we can express it as an equation, the bidirectional reflectance distribution function. The Lambertian model is an example of that. But there are many other scenarios where that information is not easily available. In other words, we know what we are dealing with, the materials that we're dealing with, but we don't know exactly what the BRDF of the material is. So in this case, we can develop what's called a calibration-based approach, a data-driven approach. That is, let's assume that you're talking about painted objects. We can take our paint and paint an object of known shape with that same paint, and then use that calibration object to create a lookup table that allows you to then take image intensity values measured on the real object, the object of interest, and map them to surface orientations or surface gradients. So after you've applied photometric stereo, what you end up with is the surface normal at each point on the object. And if the surface is continuous, we can now integrate these surface normals to recover the three-dimensional shape of the object. So we look at an elegant approach for integrating surface normal maps to obtain 3D shape.